All right, welcome everybody. So in this video and the next several videos, we are going to explore a different operation that we can apply to a matrix, namely taking the determinant of a matrix. How do we calculate determinants? Why are they useful? What information do they tell us? And as we're moving through our investigation of linear algebra this semester, we will see that determinants are a very fundamental operation on a matrix that are going to have really important consequences in many situations that we encounter. So let's return to finding the inverse of matrices, and in particular for a 2 by 2 matrix. We earlier came up with this general formula for finding the inverse of a 2 by 2 matrix, which was namely as long as the product AD, the product of the diagonal entries minus the product of the off-diagonal entries BC, as long as that is not equal to 0, then A is going to be an invertible matrix, and the inverse of A is going to equal 1 over AD minus BC times the matrix, where we interchange the diagonal entries and we change the sign of each off-diagonal entry. And if this quantity AD minus BC equals 0, then the matrix A is not invertible. So let's take a look at why this is true. So let's consider a matrix A, a 2 by 2 matrix A, where the first column is AC and the second column is BD. And so if both A and C are equal to 0, then matrix A has a column of zeros, and it is not going to be invertible, since in order for a matrix to be invertible, we know it has to have a pivot in every column. So one of A or C has to be non-zero. Without any loss of generality, let's just assume that A is not 0. If A happens to be 0, then we can just do a row interchange, right? And suddenly C would be up here in the pivot position. So without any loss of generality, we're going to assume that A is non-zero. And now let's go ahead and try and put matrix A into reduced row echelon form, or at least row echelon form. So for example, we can scale column or row 2 of this matrix by multiplying row 2 by A. And since A is non-zero, this row is not necessarily going to be zeros unless both C and D are equal to 0. And now we can do a replacement operation on row 2. I'm going to multiply row 1 by minus C and add that to row 2. And that's what's going to replace row 2. So that would give 0 beneath the first pivot. And then over here, we would have AD, and then I'm going to subtract B times C over here. And so if we assume that A is non-zero, what we can see now is that this matrix will indeed have a pivot in every column as long as this quantity AD minus BC is not equal to 0. And if A has a pivot in every column, then we know that A is invertible. And this verifies what we previously claimed about finding inverses of 2 by 2 matrices, namely, if this quantity is not equal to 0, the quantity AD minus BC is not equal to 0, then the matrix A would be invertible. And when it is equal to 0, then A is not invertible. So this quantity for a 2 by 2 matrix, when we calculate the product of the diagonal entries AD and then subtract the product of the off-diagonal entries BC, this has a lot of relevance, namely if this quantity is 0 or not 0, that's going to determine whether this matrix is invertible or maybe it is not invertible. And so this difference that we calculated, the AD minus the BC, where the AD are the product of the diagonal entries minus BC, the product of the off-diagonal entries, this quantity AD minus BC is what we call the determinant of a 2 by 2 matrix. So we apply it to a matrix, and the result of taking a determinant, we get just a scalar number back. We don't get a matrix back, we just get a number. And for the case of a 2 by 2 matrix, if that number is non-zero, then the matrix is invertible. If that number is 0, then the matrix is not invertible. And so in general, when we go up to higher dimensional matrices, it's going to be useful to write out these entries in terms of their column and row identifier. So here we could write A as A11, since it's the 1, entry, times the A22 entry over here, minus the A12 entry times the A21 entry. So here's a more general way of expressing the determinant. Okay, so now that we know how to calculate a determinant and its relevance to finding inverses of matrices in the case of a 2x2 matrix, let's take a look at a couple of examples. So the first question is asking us to find the determinant of the 2x2 matrix where the first column is 2, 3, and the second column is -4, 8. And so in order to determine whether this matrix has an inverse, we take the determinant of this matrix, 2, 3, first column, -4, 8, second column. And so by definition, we're going to take the product of the diagonal entries, which would be 2 times 8, and then we subtract the product of the off-diagonal entries, which would be the -4 times the 3. So this gives me 16, and then we've got plus 12, so altogether we have a determinant of 28. And this means that this determinant not being 0 means that A does have an inverse, and the inverse is going to be 1 over the determinant, which is 28 in this case, times the matrix. We're going to flip the diagonal entries, so I'm going to change the 8 and the 2, and we're going to change the sign of each of the off-diagonal entries. So the -4 becomes a +4, and that 3 we now make -3. And now we've got a formula for the inverse matrix of A. In question 2, we want to calculate the determinant first of the matrix that has a first column of -5, -10, and a second column of 2, 4. And depending on what we get for the determinant, then we'll see if we can find the inverse for this matrix. So here we're going to take the determinant of -5, -10, first column, 2, 4, second column. And so by definition, we take the diagonal entries, the -5 times the 4, and then we subtract from that the 2 times the -10. So over here, we get a -20. Over here, we get a +20. So they cancel. And here we can see that the determinant of this matrix is 0, so that this matrix is not invertible.